We now turn to our second property that we would like algebraic structures to have, and that is the associative property. The associative property is defined as follows. Again, we suppose that both S is a set and star is an operation. We say that star is associative on S. And this means for every set of three elements, for every three elements, A, B, and C in the member of S, for every elements A, B, C that belong to S, the expression A star B in parenthesis star C equals A star, the expression B star C in parenthesis. Now, before we go anywhere with this, it is important to distinguish commutative from associative. This is a concept that many beginning abstract algebra students get confused. Commutative involves two elements, A and B, and it says that you may replace A star B with B star A. In other words, it says you may move the order that the elements are written in. Associative, on the other hand, involves three elements, A, B, and C, and it says that you may move where the parentheses are written. Notice in the definition of associative, we're not reordering the elements. We have A on the left, B in the middle, C in the right. A in the left, B in the middle, C on the right, on both sides. Instead, we are just removing the parenthesis. So the differences are commutative is a statement that involves two elements, whereas associative is a statement that involves three elements. Commutative as a property allows you to move the order that you have written elements, whereas associative as a property allows you to move the order where you have put the parenthesis. Those are the two key differences between commutative and associative. Okay. Now, let's go back and look at our four familiar operations: addition, subtraction, multiplication, and division, and think about which two of these operations are associative on the set of real numbers. Pause the video for a second and think about it. Just like commutative, addition and multiplication are the two associative operations. Now, one of the reasons that beginning students often confuse commutative and associative is because in their high school algebra courses, both of the properties were true for the same operations. So you learn addition is commutative and associative at the same time. Multiplication is commutative and associative at the same time. It doesn't really lend itself to carefully examining the differences between what these two properties are saying, because in high school algebra, you just conceptualize these as both properties which are true. Now, what we are going to do is we are going to state the associative axioms for addition and multiplication. Just like we accepted the commutative property as an axiom for addition and multiplication, we are going to accept the associative property as an axiom for addition and multiplication. So we get the following associative axioms here. And these two axioms are addition is associative on the reals. This means that for every triple of elements A, B, and C in the reals, the quantity A plus B plus C equals A plus the quantity B plus C. And similarly, multiplication is associative on the reals. And this means that for every A, B, C, for every three elements A, B, C in the reals, A times B times C equals A times the quantity B times C. You would have seen these properties in your high school algebra textbook, probably without the scary looking for all quantifier. Now, for example, again, if we have A equals 2, B equals 3, and C equals 4, for example, if we look at 2 plus 3 in parenthesis plus 4, we do the 2 in parenthesis first, so 2 plus 3 is 5 plus 4, and that equals 9. But if we look at it the other way, 2 plus 3 plus 4 equals 2 plus 7 equals 9 when we do it this way. So notice that it didn't matter whether we parenthesized the 2 with the 3 and added those two first, or whether we parenthesized the 3 with the 4 and added those two first. We ended up getting 9 either way. And similarly, to illustrate this with multiplication, if I do 2 times 3 times 4, with the 2 and the 3 in parenthesis, the 2 times 3 is 6. So that becomes 6 times 4 is 24. But if I did this the other way, 2 times 3 times 4 is, well, we do the 3 and the 4 first. 3 times 4 is 12. So we get 2 times 12 is 24 as well. So notice again, we get the same thing, whether we parenthesize the 2 and the 3 together and then times it by 4, or whether we parenthesize the 3 and the 4 together and then times it by 2. Now, notice again, nowhere did I change the order that I wrote these. It was always 2 in the left, 3 in the middle, 4 in the right. 2 in the left, 3 in the middle, 4 in the right. 2 in the left, 3 in the middle, 4 in the right, 2 in the left, 3 in the middle, 4 in the right. Associative has nothing to do with the order that you write the elements. It just has to do with where you put the parenthesis. Now, a couple of other remarks about these examples. As with commutative, you cannot prove the associative property true just by example because the associative property has a for all quantifier. And you can't prove a statement is always true simply by listing an example of where it is true. That was the same deal for commutative. That is why we have to accept these as axioms. There are infinitely many real numbers, and thus infinitely many ways to pick 3 real numbers. Infinity to the third is infinity. So there is no way that we could verify this for every combination of 3 real numbers in our lifetime. So we have to accept these as axioms. And we do that for addition and multiplication being associative on the real numbers. In addition, and that was not a pun, but in addition, just like commutative, associative is a property of an operation. And by that, I mean, once we know that the operation, addition, say, is associative on the reals, it is automatically associative on the integers or on any subset of the reals. For example, to show that addition was associative on the integers, if you gave me integers a, b, and c, because z is a subset of r, a, b, and c would automatically be real numbers, and thus a plus b in parenthesis plus c would equal a plus the quantity b plus c in parenthesis. So like commutative, associative is a property of an operation. And associative, if it's true, if an operation is associative on a larger set, it is automatically associative on any subsets of that larger set. Okay.